Today in this class we will talk about the concept of torque. So back in the day we discussed that what changes linear motion, the change in linear motion is happen because of forces, right? So what then changes rotational motion? And that's this little quantity here called torque. Let's imagine the following. You want to tighten a bolt, so you're going to use a wrench, right? So, or you want to open a door. This is the door, these are the hinges, the door opens that way. So how do you make the door open? Well, you push with a force here. What would happen if you push with a force here? Well, not a lot. You will find it very hard to open the door if you push very close to the hinge. But if you push far away, you'll see that the door will open more easily. Same thing here. If you want to make the bolt, you want to tighten the bolt by turning it that way. If you apply a force like this, it's going to be way easier than if you apply the force like this. Also, if the force is perpendicular to the wrench, it's also going to be easier than, let's say, if you apply the force that way. Imagine trying to open the door by pushing directly in this direction, in which the line of action passes through the hinge. You will never open the door. Same thing here. If you try to push the wrench like that, you won't get any rotation. So there is a lot of elements at play here. As we can see, this distance here, the distance from the pivot of rotation to where you apply the force is important. The magnitude of the force. You won't get the same amount of torsion here if you put a big force or if you do a small force. Also, you won't tighten the bolt if the force goes in the opposite direction. Right? The angle also plays a role. So there are many things at play every time you want to do something as simple as opening a door or tighten a bolt. So the symbol for torque is the Greek letter tau, right? Tau. And it is a vector, because it's not the same to rotate something in one direction or in the other direction. And for this, we also follow the rules of the right-hand rule. But we're going to do that more in another video. Today, let's focus on the magnitude of the torque. So we have the wrench, right? And we have a force F here at an angle phi. So let's first consider this situation. You see, this force can be decomposed into a parallel component to the radius, this vector r, which it's the distance from goes from the pivot to the point of application of the force. So we can decompose F parallel or perpendicular to vector r. If we look at this, we can see that the torque is proportional to the distance r, right? And the force and also the sine of the angle. Notice, and actually this is the very definition of torque. R F sine phi, where phi is the vector between r and f, right? And then, well, r is the vector that points from the pivot, from the axis of rotation to where you apply the force. And then, well, F is the magnitude of the force. Notice that this component is the vertical component is F sine theta. The horizontal component, F cosine of theta, does nothing. It's only the vertical component times the radius. The magnitude or the component responsible for doing torque. we can switch this. Look, this is RF sine theta. So F sine theta is, of course, this vertical vector. We can look at this from a different perspective. Don't decompose the force, but decompose the R vector into a parallel component to the force and a perpendicular component to the force. If we take this imaginary line, which is the line of action of the force, we can draw a line that meets this line perpendicularly. Notice that the angle phi appears here again. This is 90 degrees. So this distance d is r sine theta. From this drawing, d is r sine theta. So once again, the torque is F and D, but D is r sine theta. Oh, sine phi, excuse me, sine phi. So at the end, we end up with the same equation. It doesn't matter if it's r f sine theta or f r sine theta, you get the same stuff. So to calculate torque, you either want the perpendicular force to R, or you want the perpendicular D to F. By the way, this D is called the moment arm. It's also called the lever or lever arm. Okay. In engineering, torque is called moment. In physics, we call it torque, but it's the same thing. And that's how you calculate the torque exerted by a force, which is what gives us the ability to change the rotational motion. This, of course, shows us why, in the example of the door, if I apply a force parallel to the door, well, you see this is the vector r. This is the force. Notice that the angle is 180. So the torque will be the r times the f times sine of 180, which is 0, so you get no torque, and the door doesn't rotate. We establish this axis here. So, and we apply two different forces. These are not central forces. So force 1 is going to try to make the potato chip spin that way, which is positively. Force 2 will try to make the potato chip spin like this, about the same origin O, which is negative. So to know what is the total effect, we calculate the total torque, which is torque 1 plus torque generated by force 2. And in this case, you see it's force times perpendicular distance, which is the lever arm already. So will be positive force 1 times d1. And then the other one is going to be negative. Well, I'm going to put it already. Negative force 2 times d2. In both cases, we already have 90 degrees. So sine of 90 is 1. So that's why I'm not putting the sine of 90. And this will be the net torque, right, acting on the potato chip. The units for torque will be units of force times units of distance, so or vector or displacement. So it will be a Newton meter. And I know that when we did work, this was a joule, but if we're talking about torque, we don't transform this into a joule. We'll leave it as a Newton meter. So consider this element composed by two different cylinders of different radii. It's a one-piece cylinder, but has two sections with different radius, radius 2 and radius 1. We have a force applied at position radius 1, which is tension 1, and then another tension 2. So what is the net torque? Well, the net torque is going to be, the net torque is going to be, well, torque 1 plus torque 2, right? So torque 1, notice that torque 1 makes our thing spin like this, and that's negative. So it's going to be minus T1 times radius 1. The other one will try to spin this like that, which is positive. So plus tension 2 radius 2. That's our net torque. If in part B we're giving the numbers, well, then we just have to substitute. Minus tension 1 is 5 newtons, radius 1 is 1 meter, plus tension 2 is 15 newtons, radius 2 is 0.5 meters. So this is going to give us minus 5 plus 7.5. So we're going to get positive 2.5 Newton meter, newtons times meters. So what does the positive mean here? It means that at the end, this whole system is going to spin like this. Oops, sorry. Is going to spin positively like this, right? So T2 wins. As usual, we will practice more. We'll practice these concepts in class later. That's it for this concept of torque.